It is indeed possible to subfeed a 120/240 volts three-phase panel with a neutral conductor. This configuration is frequently encountered in commercial and industrial buildings to accommodate the diverse power requirements of various equipment and systems. The initial service to the building being 120/208 volts three-phase indicates a three-phase power system with the voltage between any two phases is 208 volts, and the voltage from any phase to neutral is 120 volts. Subsequently, the voltage being increased to 277/480 volts three-phase signifies a transformation to a higher voltage level, typically for efficient power distribution throughout the building. In this setup, the voltage between phases is 480 volts, and the voltage from any phase to neutral is 277 volts. Finally, dropping the voltage from 277/480 volts to 120/240 volts three-phase entails a further transformation to a lower voltage level suitable for powering a wider range of equipment and appliances. In this configuration, the voltage between phases is 240 volts, and the voltage from any phase to neutral is 120 volts. The presence of both a neutral and a ground bar in the 120/240 volts panel serves distinct but equally crucial purposes. The neutral conductor provides a return path for current in 120 volt circuits, enabling the completion of the electrical circuit. The ground conductor, on the other hand, serves as a safety measure by providing a low impedance path for fault current to flow back to the source in the event of an electrical fault, thereby minimizing the risk of electrical shock. It is imperative that the neutral and ground conductors remain separate except at the main service entrance. Connecting them together at any other point can create a hazardous condition, potentially leading to stray currents and increasing the risk of electrical shock. Here's a more detailed breakdown of the concepts involved. Firstly, understanding the different voltage configurations is key. A 120/208 volts three-phase system is a Y-connected system where the voltage between any two phases is 208 volts, and the voltage from any phase to neutral is 120 volts. This system is commonly used in commercial buildings for lighting, receptacles, and other general-purpose loads. A 277/480 volts three-phase system is also a Y-connected system, but with higher voltages. The voltage between phases is 480 volts, and the voltage from any phase to neutral is 277 volts. This system is typically used for larger loads such as HVAC equipment, motors, and industrial machinery. A 120/240 volts three-phase system is a delta-connected system with a center tap on one of the windings. The voltage between two of the phases is 240 volts, and the voltage from either of those phases to the center tap is 120 volts. The voltage from the third phase to either of the other two phases is approximately 208 volts. This system is often used in light industrial and commercial applications where both 120 volts and 240 volts power are required. Secondly, let's talk about subfeeding a panel. Subfeeding a panel involves taking power from an existing panel and feeding it to another panel. This is often done when there is a need for additional circuits or when the existing panel is located far from the loads that need to be powered. When subfeeding a panel, it is important to ensure that the feeder conductors are properly sized to handle the load. The feeder conductors must be sized according to the National Electrical Code, specifically Article 215. In addition, the subfed panel must have its own grounding system, separate from the grounding system of the main panel. This is to prevent circulating currents and ensure that the ground fault protection system functions properly. Thirdly, the neutral and ground conductors play very different roles. The neutral conductor is the return path for current in a circuit. In a 120 volt circuit, the current flows from the source through the load and back to the source via the neutral conductor. The neutral conductor is typically connected to the neutral point of the power source, which is usually grounded. The ground conductor, on the other hand, is a safety conductor. It provides a low impedance path for fault current to flow back to the source in the event of an electrical fault. This allows the overcurrent protective device, such as a circuit breaker or fuse, to quickly trip and to energize the circuit, preventing electrical shock. The ground conductor is connected to the equipment grounding system, which includes all metal enclosures, conduit, and other non-current carrying metal parts of the electrical system. The neutral and ground conductors should only be connected together at the main service entrance. This is the point where the power enters the building. At this point, the neutral and ground conductors are bonded together to create a single point of reference for the electrical system. Connecting the neutral and ground conductors together at any other point can create a dangerous situation. This can cause current to flow through the ground conductor, which can lead to electrical shock. In addition, it can interfere with the operation of ground fault circuit interrupters, which are designed to protect people from electrical shock. Fourthly, sizing the feeder conductors is very important. To properly size the feeder conductors for a sub-fed panel, you need to determine the total load that will be connected to the panel. This includes all of the lighting receptacles, appliances, and other equipment that will be powered by the panel. Once you have determined the total load, you can use the National Electrical Code to determine the minimum size of the feeder conductors. The National Electrical Code provides tables that specify the ampacity of different sizes of conductors. Ampacity is the maximum amount of current that a conductor can safely carry. When sizing the feeder conductors, it is important to consider the voltage drop. Voltage drop is the decrease in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or not operate properly. The National Electrical Code recommends that the voltage drop in feeder conductors should not exceed 3%. Fifthly, grounding and bonding is also important. Grounding and bonding are essential for electrical safety. Grounding is the process of connecting the electrical system to the earth. This provides a low impedance path for fault current to flow back to the source in the event of an electrical fault. Bonding is the process of connecting all of the metal parts of the electrical system together. This ensures that all of the metal parts are at the same potential, which reduces the risk of electrical shock. The grounding system for a sub-fed panel must be separate from the grounding system of the main panel. This is to prevent circulating currents and ensure that the ground fault protection system functions properly. The grounding system for the sub-fed panel should be connected to a grounding electrode, such as a ground rod or a metal water pipe. In summary, sub-feeder 120/240 volts 3-phase panel with a neutral is a common and acceptable practice in commercial and industrial buildings. However, it is important to follow all applicable codes and standards to ensure that the installation is safe and reliable. The feeder conductors must be properly sized, and the sub-fed panel must have its own grounding system. The neutral and ground conductors should only be connected together at the main service entrance. By following these guidelines, you can safely and effectively sub-feed a 120/240 volts 3-phase panel with a neutral. It is critical to consult the National Electrical Code, specifically Articles 215, 250, and 408 for detailed requirements regarding feeder sizing, grounding, and panel board installation. Additionally, local electrical codes and regulations may impose further restrictions or requirements that must be adhered to. The following points should always be kept in mind. Firstly, always consult a qualified electrician. Electrical work can be dangerous, and it is important to have a qualified electrician perform any electrical work that you are not comfortable doing yourself. Secondly, follow all applicable codes and standards. The National Electrical Code and local electrical codes provide detailed requirements for electrical installations. It is important to follow these codes to ensure that the installation is safe and reliable. Thirdly, use the correct materials. Use only materials that are listed or labeled for the intended use. This will help to ensure that the installation is safe and reliable. Fourthly, inspect your work. After you have completed the electrical work, inspect it carefully to ensure that it is done properly. Look for any loose connections, damaged wires, or other problems. If you find any problems, correct them immediately. Fifthly, test your work. After you have inspected your work, test it to ensure that it is working properly. Use a multimeter to check the voltage and current in the circuits. Also, test the ground fault protection system to ensure that it is working properly. Sixthly, document your work. Keep a record of all of the electrical work that you have done. This will be helpful if you ever need to troubleshoot a problem or make changes to the electrical system in the future. This record should include a wiring diagram, a list of materials used, and the dates that the work was performed. Lastly, remember to prioritize safety above all else when working with electricity. Always energize circuits before working on them and use appropriate personal protective equipment, such as gloves and safety glasses. By following these safety precautions, you can minimize the risk of electrical shock and other injuries. In addition to the points mentioned earlier, there are a few other considerations to keep in mind when subfeeding a panel. One important consideration is the available capacity of the existing panel. Before subfeeding a panel, it is important to ensure that the existing panel has enough capacity to handle the additional load. This can be determined by calculating the total load on the existing panel and comparing it to the panel's ampacity rating. If the existing panel does not have enough capacity, it may be necessary to upgrade the panel or install a new panel. Another consideration is the location of the subfed panel. The subfed panel should be located as close as possible to the loads that it will be serving. This will minimize the voltage drop in the feeder conductors. The subfed panel should also be located in a dry and accessible location. In addition, it is important to ensure that the subfed panel is properly labeled. The label should clearly indicate that the panel is a subfed panel and should identify the panel that is feeding it. This will help to prevent confusion and ensure that the correct panel is de-energized when performing maintenance or repairs. The National Electrical Code provides specific requirements for labeling subfed panels. These requirements are outlined in Article 408.4. The label must be permanently affixed to the panel and must be legible. It is crucial to thoroughly understand the relevant sections of the National Electrical Code and to consult with a qualified electrician to ensure that the subfeeding of the panel is performed safely and in accordance with all applicable regulations.